Good afternoon and welcome to today's Machine Design webcast. Our topic today, an introduction to actuators and how to integrate them to decrease your time to market. It's being sponsored by Harmonic Drive. My name is Steve Miraz with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of the screen. Additionally, we welcome your question during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when it is available. Now let's meet today's speaker. Andrew Zucker is a mechatronics engineer at Harmonic Drive. Before joining the Harmonic Drive team 4 years ago, he studied electromechanical engineering at the Wentworth Institute of Technology. In addition to his degree, Andrew participated in competitive robotics, including the first and mate ROV competitions for 9 years. With his industry experience in competitions, he has worked in robotics for 13 years. Now let me turn things over to our presenters. Andrew, the floor is yours.
All right. Thank you, Steve. Thank you, everyone, for joining us today. So let's get started. So today we have an introduction to actuators and how integrated actuators decrease your time to market. I'll start us off with an agenda here. First, we'll have a company and a product brief, and then go into an intro to advanced motion control applications. Then we'll do a deep dive into actuators and their construction and components, and then we will finally explore how to decrease your time to market by utilizing actuators with integrated servo drives. And then we'll get to some questions and discussion at the end. So who is Harmonic Drive? Harmonic Drive engineers and manufactures precision servo actuators, gearheads, and gear component sets. We work closely with both Fortune 500 and companies of all sizes to understand their application requirements and provide standard or custom engineered solutions to enable the success of their design project. So below we have a couple of applications that our products were used in. How did we begin? Harmonic Drive began with an inventor named C. Walton Musser, who came up with a concept for a new type of gear in the 1950s. Musser and Harmonic Drive developed the world's first flexible gear design, known as a strain wave gear. This design uses flexible mechanics compared to rigid mechanics. Harmonic Drive strain wave gearing revolutionized motion control and is a common solution for high precision and high torque applications. So in 2023, Harmonic Drive has a global presence. Our strain wave gears are made in 3 countries to support our local regions, with Japan having multiple sites. So I'm talking to you today from the Beverly, Mass headquarters of the United States. Some of the typical industries that we serve include the robotics, aerospace, medical, automation, defense, semiconductor, machine tools, and many other industries. Again, we have a few applications shown below. So next, I'd like to show a video that explains the operating principle of a strain wave gear. So you should see that being sent to you now.
High-precision, zero-backlash harmonic drive gear component sets are key to the performance of our gearheads and servo actuators. Harmonic drive component sets consist of only 3 precision components: wave generator, flex spline, and circular spline. The wave generator is the driven or input element of the transmission. A hub having an elliptical shape is fitted within a special thin raced ball bearing to create the wave generator. The flex spline is a robust, torsionally stiff, yet radially compliant component with external gear teeth, capable of reliably transmitting high torque loads. The circular spline is a rigid ring with internal gear teeth. The circular spline has 2 more teeth than the flex spline. When inserting the wave generator into the flex spline conforms to the elliptical shape of the wave generator. Rotating the wave generator creates an advancing waveform on the flex spline. When assembled with the circular spline, tooth engagement occurs at each end of the major axis of the ellipse, and up to 30% of the total number of gear teeth are simultaneously engaged. The rotation of the wave generator causes the flex spline and circular spline tooth mesh to move around the circumference. Since the flex spline has 2 less teeth than the circular spline, rotation of the wave generator leads to a relative movement between the flex spline and the circular spline. Harmonic drive component sets, gearheads, and servo actuators are used wherever zero backlash, extreme precision, and high reliability motion control is required. Harmonic Drive, advancing the technology of motion control through innovation.
All right, so now that we have a basic understanding of how the strain wave gear works, let's talk about some of the advantages, and then we'll see how this applies to actuators designed using strain wave gears. So the major advantage of a strain wave gear is it has zero backlash. This is because of its high percentage of tooth engagement that allows an interference fit around the teeth. They also have excellent positional accuracy and repeatability, where the accuracy is typically less than 60 arc seconds. A normal spec is 30, and the repeatability is approximately on 5 arc seconds. Strain wave gears have high torque density because of their compact design, and their gear ratios ranging typically from 30:1 all the way to 160:1 can be made with the same outline dimensions, so there's no change in weight or form factor. Also, the inline configuration of the strain wave gear allows hollow bore capability. You can see in the bottom right side a very large hollow bore. Harmonic drive strain wave gears also have high torsional stiffness, and the high gear ratio units also have a back drive capability, which is uncommon for very high gear ratio gearboxes. So now let's define advanced motion control for the context of this presentation. In advanced motion control, you require a mechanism or system with the characteristics of positioning accuracy less than 100 arc seconds, high repeatability less than 10 arc seconds, and below I just have a graphic here that shows the true scale of arc seconds. So starting from the left, we have a circle, and we have 2 lines that signify 1 degree. Then moving to the right, we have zoomed in and divided that 1 degree into 60 equal increments. These are known as arc minutes, and there are 60 of them in 1 degree. Then we zoom in further on these increments, dividing each increment into a further 60 equal increments. This is known as an arc second, and there are 3,600 arc seconds in 1 degree. So we're talking about a very fine scale here. If you convert back to degrees, it is 0.00027 degrees per arc second. So in addition to this, to have advanced motion control systems, you typically also need high moment stiffness, which is resistance to load perpendicular to your axis of rotation, high torsional stiffness, which is stiffness in the same axis as your rotary application, the ability to execute complex motion paths, which you'll see in the next slide, multi-axis coordinated motion, typical for robotics applications, and capable of precision motion with variable inertia loads. So to put advanced motion control in context, I will use robotics as a lens here. So robotic joints typically consist of servo actuators, and there are mechanical, electrical, and controls components that make up the entire motion control system. So in the middle center, we have a robotic workspace. This robotic arm has, I believe, 6 axes, and you can see the dark gray dotted line is all of the locations in this plane that the end effector can be positioned at. So all of the movements in between to any point in this gray area would be a complex motion path. So let's dive into actuators. Starting from the highest level, we have a electromechanical system that is called an actuator. This device converts electrical power into mechanical torque using an electric motor. The output torque is amplified by a harmonic drive gear, and the system's position is fed back to the servo drive on the right through 1 or 2 feedback encoder devices. Actuators also typically include an output bearing to support moment loading and seals to protect against harsh environments. The servo actuator is connected to the servo drive, usually through 2 cables, one for the motor's power and another for the feedback and signals. So let's take a bit of an electrical view here to show what all of the signals are actually doing. So from the left side, we have that servo drive again, which contains all of the feedback controls. It controls the trajectories, and it also has a power stage that controls the motor. So moving forward on the right, first we have motor position feedback, which is always coupled to the motor. And if you look at the top of this diagram, we have encoder signals feeding back to the drive electronics or the servo drive. And we have Hall sensor signals coming from the motor, feeding back into the drive electronics. Feeding out of the drive electronics on the bottom of the screen, we have the connections for the motor phases, and these are what supply current to the motor so that it can generate mechanical torque. Then, moving to the right of the motor, we amplify the torque output using gearing. And in some applications, there's a secondary encoder coupled to the output of the gear that is fed back to the drive electronics so that you can have extra functionality by knowing the gear output's position. So all of these electrical systems are controlled using feedback. You can see on the left here, I have a very slightly different diagram. We still have the drive electronics on the left side, the motor phases feeding the motor towards the right, and we have 3 control loops next to each other on the right side. The first, from left to right, is motor current control. So the drive electronics have a feedback loop that reads the motor current. You can see that on the top. We have current feedback signals feeding into the drive electronics. Then next to that, we have motor position control. The motor position control comes from the encoder, which I'll go over in more detail soon. And that is used to control the output position. Then we have motor velocity control. All of these parameters can be used in different applications depending on your needs. All of these control loops are generally proportional and integral control loops. So they have a P and an I gain. These are typical in control systems, and you can see below I have drawn a step response. So a step response is a usual way to calculate a system's response to a signal, and that is appropriate for all 3 of these control loops that I have shown on the left side. These loops are usually tuned per your application. So if you have a high inertia load or if you have a low inertia load, you would need different control gains for your control loops. Another thing that's usually measured in a system that requires control is the bandwidth. So this is usually done with a Bode plot, and I don't have a picture of that to share with you right now. One thing I'd like to add is that typically the current control is much faster than the position and velocity control. and this is typical for actuators. Now I will show a couple of basic form factors that you may see. The first is a hollow shaft. So these are usual in robotics applications for passing wires, shafts, tubing, and other similar things through the center of the actuator. In the center here, we have a flat form factor. This could be described as a diameter that is wider than the length of the actuator. And on the right side, we have a cylindrical actuator, which also has a hollow shaft. And the diameter in this case is smaller than the overall length. There are other form factors, such as right angle, but I don't have pictures of those to share. So let's dive into the rest of the components that make up an entire actuator, and then we'll carry on. So the first component, as I've already described, is a strain wave gear. Strain wave gears are an exceptional choice for actuators because of their high torque density and because of their form factor. There's a few ways to determine which strain wave gear is right for your application. One of them is by using a benchmark calculation that is called torque density. So in this case, I have two calculations that I'm calling torque density. One of them is taking the rated torque capacity of the strain wave gear, dividing it by the volume that the strain wave gear takes up. Another calculation that can be used if you're more concerned about weight in your system is to take the rated torque capacity and divide by the weight of the device. And as we already know, the strain wave gear also enables hollow shaft designs, and it simplifies your design for a variety of ratios. This means that you can design a single actuator and change out the gear ratio as needed so that you can fine-tune your output torque and output velocities. The next most important component is the motor. There are many common types of motors that can be used. In precision actuators, there's a few that you would see more than others, which is why I've only listed 3 here. The first you might see is a brushed motor, which I'll go into more detail on all of these after this slide. Then we also have stepper motors and brushless motors. Some of the important design factors that need to be considered when designing an actuator is size, weight, the torque and efficiency curves of the motor, and the coil voltage. This choice affects your gear selection. You should match the torque of the motor so that it can drive the gear. And you should match the motor winding with the servo drive's operating voltage. So a brushed motor uses carbon brushes to transmit power to the windings on the rotor. Some of the advantages include that they are inexpensive and they're easy to control. Some of the disadvantages include their decreased efficiency due to the brush friction. The brushes wear out over time and require replacement. The brushes can spark, creating EMI in your system or electromagnetic interference. And these motors typically have high inertia because the dense copper coils are on the rotating component of the motor, as you can see on the right side. Next up, we have stepper motors. A stepper motor divides a full rotation into a number of equal steps by using toothed electromagnets. You can see on the right here that as the coils are energized, the rotor moves one increment at a time as it's attracted to the next coil through its teeth. Some of the advantages of stepper motors include that they are inexpensive. They operate in open loop, so they don't require feedback. They're easy to control by using incremental steps. And they have full torque at 0 speed, which is useful for holding applications. Some of the disadvantages include their large torque loss at high speeds, resonance or ringing being introduced into your system if the operation is too fast, and they typically have lower efficiency. And next, the most complex of the 3 is the brushless motor, which uses electronic commutation and a feedback device to move. The advantages of a brushless motor include that they are quiet, high efficiency, have a long life due to no touching components, have a high torque to weight ratio, have near instantaneous torque and speed control thanks to their feedback device and electronic commutation, and they can be available as a frameless motor kit, which provides you the ultimate flexibility in creating an actuator system. In the bottom right side, I have a picture of a frameless motor installed into a housing, and it has on the inside, the rotor is coupled to a custom motor shaft. Some of the disadvantages of a brushless motor include their higher cost and that they require feedback and a servo drive. So next on our list here is the feedback. If you've been following along closely, on the right side, we kind of have a cross-section of an actuator, and there's a blue highlight that's changing to show where these components are usually placed. So when it comes to feedback, there's many, many options. Some that I don't have listed here are potentiometers, which are similar to knobs that you can control, and resolvers, which are used in very high reliability situations, such as aerospace and defense applications. But here, I'll just talk about feedback devices known as encoders, and there's two typical types of encoders. There's an absolute encoder, where each count around the encoder is unique, so each position gives you a new piece of data. And there's also incremental type encoders, where each count along the revolution is relative. So incremental encoders always require homing and an index to know where they are at any time. Absolute encoders, depending on their construction, either single turn or multi-turn, will know their exact position on power up, but to the precision to which they're known, whether it's single turn or multi-turn, depends on the type of encoder. So for multi-turn encoders, there's a few ways to actually get the multi-turn capability. One of them is by using a geared component inside of the encoder that keeps track of multiple turns using a gear ratio. You can also use a battery that stores multi-turn data through power loss. So when you turn your system off and back on, the battery keeps your multi-turn data intact. And a newer solution that has been becoming more popular is wagoned wire, which is a energy harvesting technology that can be used to passively count multi-turn revolutions. Almost all of these encoders are available in multiple technologies. Some of the most common I have listed below. There's optical, which uses light. There's magnetic, which of course uses magnets. There are capacitive, which use the capacitive effect. And there are inductive encoders, which use the inductive effect. All of them have their own advantages, with optical being usually the most precise out of all of them, but the most sensitive to environmental effects, and the others can be used in different applications. So if you remember back from the control loops, we have load position in some cases, load position feedback. The benefits of using a single turn absolute encoder on the output, in addition to a single turn absolute encoder on the motor, include that there's no homing required within one revolution of the output, because you've fully defined your system from the output and from the motor. And you gain increased safety and reliability in your system by the redundancy through multiple encoders, which give you fault recognition. And within a single turn, you have a batteryless multi-turn solution for your motor. So the remaining components that I have here, I can't go into much detail because I do have many more things to talk about, but other things that are included in actuators are the output using cross roller bearing. So typically on the output, you'll have a cross roller bearing to support moment loading, seals to support environmental effects, motor shaft and support bearings, and of course the housings that hold everything together. And in some cases, we have safety brakes as well, which prevent operation when not powered. So now let's get into the actuator component known as the servo drive. This is more of the brains of the system that tells the actuator what to do. So servo drives include many functions, some of which include feedback control loops, They are capable of controlling the actuator in various different control modes, and many also include extra IOs or inputs and outputs to control or read external devices. Some common concerns include cabling and space concerns. So we'll start with the functions, then we'll focus back in on the concerns after. So feedback loops, we've already gone through these. Current loops, position loops, and velocity loops are all included and calculated and monitored within the servo drive. And some other control modes that you can see abbreviated here are cyclic synchronous torque, cyclic synchronous velocity, and cyclic synchronous position. This control method takes the burden of trajectory planning off of the servo drive and relays it to the controller that is controlling the servo drive. So what that does is it sends out adjusted control parameters to all of the axes in a system at a regular interval, which helps keep all of your axes in sync in real time. When it comes to cabling, you need to provide power to the servo drive from either AC or DC power bus. You need a way to communicate with the servo drive. This is typically another communication cable that is added into your system. And if you have safety connections or other IOs, they must be appropriately wired to the servo drive. So including the motor and encoder cables that are needed to control the actuator, there could be up to 5 cables for each axis in your systems. So many servo drives can be large to accommodate all of the connectors as shown, but many servo drive manufacturers have been miniaturizing to meet today's needs. Here I have a typical servo drive panel where you can see all of the space that's taken up for about 15 axes of motion. You can see all of them have multiple cables going into them and a very large control box surrounding them. So this is the entire servo system. We have the actuator on the left side, the servo drive on the right side, and in the middle we have cables that connect them. But this does not mean that we're done after we've designed and selected all of these components and put them together. We still have to introduce them to each other and get them speaking the same language, which in the industry is known as commissioning. Commissioning includes many steps, including setting your motor parameters and limits, where some of the typical values are shown here. You have to set your encoder feedback protocol, and you have to confirm your phase sequence for proper directional control. And then if we remember back to the control loops, we have to tune those, and we like to measure our bandwidth so that we know the capabilities of our system. When it comes to cabling on actuators, pigtail cables are typical on motors, and a common concern is the flex rating of the conductors. In flexed applications, cables have a finite lifetime. The lifetime is decreased with a smaller bend radius. When you have larger cable bundles, this forces some of the cables to have a tighter bend radius if they're on the inside of the bundle. And because there's a mismatch between the inside radius and the outside radius, there is an amount of chafing that occurs between the cables in a bundle. So, with this being known, routing of large cable bundles can be challenging and makes cable replacement difficult. Here I have shown some typical sizes for the cables that are used in actuator systems. On the top, we have a single motor and single encoder cable for one axis of motion. Below, I have combined 6 of those into their own respective bundles with motor power cables on the left and encoder feedback cables on the right. When these cables are bundled together, we end up with almost an inch diameter for each of these bundles. On the left side of the screen, we can see the picture here of a robot completely full of wires. And on the right side, we have another application that has about 6 axes of motion and all of the cables returning to their servo drives, which are then returning to their controller. So with all of that being said, we've introduced a system-level view of a generic servo actuator system. And unfortunately, there's a long list of other topics that we won't get into today. You can see those below. But most projects don't have the timeline to actually start from this base level because it is a lot of work. So with that, I would like to introduce integrated servo drives, where the servo drive is inside of the actuator itself. So with all of those things being said, we've just put the servo drive and all of the connecting cables under the cover of an almost identically sized actuator. Some of the benefits of integrated servo drive actuators are that they are plug and play, which means that they're modular devices. They have a minimized cabling requirement. All you need is power and communication to the servo drive. Everything else is handled. They have enhanced cable serviceability thanks to their pluggable connectors. They're easily scalable as well thanks to their minimized cable requirement and bus capabilities. They have a localized connectivity feature, also known as remote I/O. They can decrease your total system size and mass, and in some cases, they are customizable. So a little more detail on this. The plug-and-play solution, servo drives with integrated actuators are fast and intelligent. Their standardized connectors afford a physical plug-and-play connection. So if you have to change your size from one to another, odds are you can just unplug the cable and plug it back in to the new one. And the intelligence of them is that they already contain all their relevant actuator parameters, which allows you to skip the commissioning step that's needed for conventional servo systems. So here I have kind of an inside-out view of all of the signals that are needed for a conventional servo system. On the left side, we have our line driver incremental encoder with Hall signals. In the center, we have a three-phase motor with a safety brake and a safety ground. And both of those are feeding back on the right to a servo drive that has input communication, output communication, and is connected to a DC power bus. So all of that goes back on the far right side to the controller. This is typically a PLC or a PC, depending on your application. And let's see how integrated servo drives will minimize this wiring requirement. So since the servo drive is inside, we've eliminated all of the extra wiring for the encoder and the motor. That's connected directly to the servo drive. So the only wiring that is needed is power and communication back to the top level controller. This is done in a single cable. Because of this single cable, you have scalability built in. So due to the communication bus that can be used, you can have up to 127 axes on a single power and communication bus. That is shown below. So to put this in other words, on the left, I have a conventional servo system with 3 axes included. And on the right, I have an equivalent integrated servo drive system. On the left, from the conventional system, you can see that it scales linearly with each axis added. So each axis has 2 cables that go to the servo drive and 2 more that go to the controller and to the power supply. This is needed for each new axis. On the right side, with integrated servo drives, we have a power and communication bus that is jointly connected to the controller and to the power supply, and can either be bused or daisy chained between each new axis. So this is a nonlinear scaling where you're only adding a new motion axis and a connecting cable to your bus or to the last axis. When it comes to connectivity, you gain access to remote I/O capabilities, which means that you can connect industry standard sensors directly to the actuator, and you can use these standardized sensors over the 2-wire communication bus that the actuators communicate on. This also helps eliminate extra cabling through the system even further. On the left, we have that conventional servo system where a sensor has been added onto the end effector and has to be routed all the way through the system back to the controller. On the right side, we have the integrated equivalent system, and this has a sensor that is plugged directly into the closest axis. This saves on your cabling. So thanks to their servo drives being under the cover and thanks to their minimal increase in size, there's no need for external servo drives, and this eliminates multiple cables from each motion axis. So this saves you all of this room in your application and allows you to have this free space freed up for something else. So with all of this being said, how do we decrease our time to market? So I'll go into all of these in a little bit more detail, but from a general standpoint, you use existing components to shorten development time, simplify your design by using actuators with an integrated servo drive. You eliminate time-consuming tasks like commissioning and wiring, and you utilize modular building blocks. And finally, you focus on your core competencies. All of these things together will help you decrease your time to market. So what does this mean, use existing components? Well, it means that you can spend your valuable R&D time on creating a new system and not on the subsystem components. This allows you to build on top of proven solutions to create a new system more efficiently. And finally, it allows you to decrease your system cost and your R&D time by using complete products that have been optimized for mass production. So on the right, we have kind of a pyramid here where you could start from the component level, where you go through and specify your gears, your motors, encoders, all of these things. You go through the design cycle, and you go through all of your testing. The next level up is that you can use existing components, such as servo actuators, put those together in a configuration that you need, and that helps you build your new system. The second tip I have is to simplify your design by using actuators with integrated servo drives. So eliminate external components like servo drives and cables from your system. This will decrease your overall system size and the complexity. You can simplify your cable requirements to a single cable for each actuator. And you can utilize more efficient connection topologies like a bus or a daisy chain. So I mentioned those a little bit earlier, but now I have a graphic to show you. All the way in the right side corner, we have a star configuration, which is the only way to connect your conventional servo systems together. The next tip I have for you is to try to find ways to eliminate time-consuming tasks like commissioning and wiring. So commissioning a drive, as we saw earlier, can be a lengthy process of checking and configuring multiple settings in a servo system. You can eliminate that by using actuators with integrated servo drives because they've already included the commissioning step. When building a conventional servo system, it can be necessary to manually wire up to 20+ conductors for each axis, as you can see in the bottom left side. And by using integrated servo drives, you can limit all of that wiring down to just 4 conductors. The next tip I have is to utilize modular building blocks. What this means is to use things that you can switch out easily to buy yourself upgrade capability if your system needs to grow in the future, and versatility in case you calculated your torques wrong, or you need different gear ratios, or if you need full different size actuator to be placed into your system. So just like that, you can change out your axes. And the final tip I have for you today is to focus on what you do best. Delegate your non-core competencies like advanced motion control subsystems to industry experts like us at Harmonic Drive. You can leverage over 60 years of design experience, and we're happy to help. So with that, I will leave you with one word to stick: simplify. And with that, I will turn it back over to my friend Steve. Steve, are you there?
Okay, so I don't see Steve on the line. I don't know if he dropped off, but I will start with one of the questions that we have. If you do have any questions, please put them into the Ask a Question box on the side of your screen, and we will get to them as soon as we can. The first question is, are there EMI concerns from combining the power and communication lines into a single cable?
Thank you for the question. That's a very good question. Currently, there are no EMI concerns for combining the power and communication lines into a single cable. This is because the communication lines use a twisted pair differential communication bus, which cancels out any of the EMI generated from the power supply lines.
Okay, what is the maximum actuator load? Is the integrated solution customized for specific customer features?
Thank you for the question. The maximum actuator load, the largest that we have is equivalent to one of our products that is called an SHA-32, which has, I believe, a rated load of approximately 500 Newton meters. I would have to confirm on that, but I'm fairly certain that that's the number. The integrated solution is customizable to an extent for customer applications. They're based on a standard product line that we have available now. If you have a custom application that you would like to see if we can help you out with, feel free to reach out to our sales engineers, and we'll get you started.
All right. What is the size difference compared to an equivalent actuator?
So in terms of size, I think our worst addition is a localized bump for the connectors of 6 millimeters. In terms of total cover addition, one of our sizes called the FHA-11, I believe, has about a 3 millimeter cover extension added to the size of a standard actuator.
All right. Is there an EtherCAT option on the integrated servo drives?
At this time, there's currently no EtherCAT option, but that is an upcoming feature that we're hoping to release soon.
All right. Do any of these integrated drive actuators have a brake built in?
Yes, the larger of the series has a brake built in by default and is also available with no brake.
Okay. What communication standards can be used?
So the only one that's available, well, actually there's two. CAN open is the preferred communication profile, and they're also capable of being controlled over a standard CAN. We're hoping to work with EtherCAT soon, as I mentioned before, but that's currently not available.
Okay. What method is used to get velocity feedback?
So the velocity feedback is derived from the position feedback. So just by using a simple encoder feedback, we're able to calculate velocity loops.
Okay. What is the maximum actuator load, and is the integrated solution customizable for specific customer features?
I believe I already answered that one, but I'd be happy to answer that again. Just let me know.
Okay, we'll move on. What is the typical output accuracy when using an output encoder?
So depending on the output encoder that you're using, that can vary. When it comes to these actuators, their output resolution is, depending on the size, it ranges from 14 bits to 16 bits of resolution.
Okay. Do you have any software modules that can be used for programming multiple axes for coordinated motion?
In terms of an all-in-one software solution, we offer a tuning software where you can use multiple actuators in the same program, but this is, I would say, not particularly suitable for advanced motion control profiles of multiple axes. So to put that short, no, we don't have a software module, but yes, we do have a Python library, and we also, I believe, have capability to assist in writing TwinCat code, or at least we have capability to use TwinCat, which is a feature of Beckhoff PLCs.
All right. Can you use these devices in high pressure environments such as wind tunnels, such as in a wind tunnel test section?
Interesting. That I actually don't know the answer to at this time, but I would love to do a little bit of research and get back to you on that one.
Are there any other environmental limits to where they can be used, for example, temperature or underwater or any others?
Yes. So generally, these are rated for under 1,000 meters of elevation, so they can't be used very high up. They are rated for, I believe, 30 Gs of vibration. They are rated for 0 to 40 degrees Celsius continuous operation. What else? I believe they're all IP54. So they're not suitable for underwater use, but they are protected against incidental splashing and things of that sort.
Okay. That seems to be all the questions we have. So that would conclude today's presentation. On behalf of Machine Design, I'd like to thank Andrew for an excellent presentation and Harmonic Drives for sponsoring it. And of course, all of you, thank you for joining us and have a great rest of the day.